So maybe I'm curious to ask you if you can tell us about what's actually geometric nonlinearities, because I think many episodes, few guests just stressing the point how we can couple the geometric and material nonlinearities so that we can have interesting information, and it could be also replace the traditional control techniques. But still not many people in the community agree with that, or maybe still not see this kind of vision by some researchers in the field. Since you work in geometry and you're really interested in that, how you can get or extract this beneficial geometric nonlinearities?
So the way I think about it is that we use geometric design in order to create non-linearities, right? I think there's a lot of work in linearizing systems, which has really gotten us very far in terms of creating new designs, creating really good controllers, creating really good models. But they don't capture the whole performance of the system. And we try to force the system to follow whatever linearization that we've created, because that makes it easy to model or because it makes it easy to control, then we lose a lot of the potential of the design, right? So if you take advantage of the nonlinearities in a system, then you can potentially get a lot of complex behavior for free. And what we're really interested in is then, well, how do you tune the geometry of a structure, or how do you choose the mechanical properties of a structure in order to get the particular nonlinearities that you want? I don't know if that answers your question.
Yeah, and do you think about how we can couple that with material nonlinearities? If you speak about what you say, do you think there's something different, or could be changed significantly in the performance if you couple that with the material itself as a nonlinear material?
Sure. I mean, nonlinear materials are extremely important, especially in soft robotics, right? If you have a linear material that you can model as a linear spring, that's great, right? That you can create all sorts of really interesting structures. But if you have materials that are nonlinear, like softening materials, materials that become softer as you stretch them more, or materials that become harder as you stretch them more. There are materials that increase in damping as you stretch them more, right? These materials allow you to have the robot's performance change automatically as it's moving, right? So for example, if you want to create a robot that's has multiple different soft components, but you want them all to kind of come to an equal level, right? An equal distance or equal amount of compression, and you have this material that increases in stiffness as it compresses, then that's an inherent controller in the system, right? As you compress the structure, different amounts of force on different areas of the robot are going to induce different amount of compression. But because the material properties change as the material compresses, then eventually all of the compression might balance out, right? And so this is a way, by using nonlinearities in a material, you can embed some sort of mechanical intelligence into the structure itself, right? And not have to put an external controller on top of it, which reduces your control complexity. It increases your modeling complexity, right? But it does allow you to put some sort of very interesting behavior and internal control into the robot body.
Yeah, thanks a lot for mentioning that. I think you say it in a very simple way and concrete as well. So thanks a lot for saying that.